Welcome back to Global Works TV, where we explore the fascinating world of industrial manufacturing and the incredible machinery that powers modern production. Today, we're taking you on a journey to New Zealand to discover how one of the industry's most respected operations transforms raw timber into finished products through some of the most sophisticated sawmill and pulp processing systems in the world. Winstone Pulp International, or WPI as it's known throughout the forestry industry, has been a cornerstone of New Zealand's timber processing sector for decades. What makes their operation particularly interesting is how they've integrated two complementary facilities, the Tangiwai Sawmill and the Karioi Pulp Mill, to maximize efficiency and minimize waste. It's a philosophy that would have made the old-time sawyers proud, though they'd hardly recognize the technology we're about to explore. Let's start at the Tangiwai Sawmill, where the journey begins. This facility primarily processes radiata pine, a species that's become synonymous with New Zealand forestry. Now, if you're wondering why radiata pine, here's an interesting bit of history. This tree, native to California's coastal regions, found its perfect home in New Zealand's climate back in the 1850s. Today, it grows faster and straighter there than almost anywhere else on Earth, reaching harvest size in just 25 to 30 years, compared to 80 to 100 years for many Northern Hemisphere species. When logs arrive at Tangiwai, they first encounter the debarking system. This isn't your grandfather's manual debarking process. Modern ring debarkers use powerful hydraulic arms with carbide-tipped teeth that rotate around the log at high speed, stripping away bark in seconds while the log moves through at a steady pace. The stripped bark isn't wasted. It's collected and used as biomass fuel to power the facility's operations, a practice that's both economically smart and environmentally responsible. After debarking, logs enter the metal detection station. You might think this is overkill, but here's why it matters. A single piece of embedded metal, perhaps from an old fence post that grew into the tree, or hardware left from forest management operations, can destroy an expensive saw blade in milliseconds and halt production for hours. The metal detectors use electromagnetic sensors that can identify ferrous metals deep within the wood fiber, and pneumatic kickers automatically divert any suspicious logs for manual inspection. Now we reach the heart of the operation, the main breakdown saw. Tangiwai utilizes a profile optimization system that's genuinely remarkable. Before each log enters the saw, laser scanners create a three-dimensional digital model of that specific log, identifying every curve, taper, and defect. A computer algorithm then calculates, in fractions of a second, the optimal cutting pattern to yield the maximum value from that particular piece of timber. This technology has revolutionized sawmilling efficiency. Where old-time sawyers relied on experience and eyeballing the log, modern systems can improve yield by 15 to 20%. The primary breakdown saw itself is typically a bandsaw or circular saw configuration, depending on log diameter. Bandsaws, with their thin curve, that's the width of the cut, waste less wood, but require more maintenance and skill to operate. The saw carriage moves the log through the blade with precision measured in fractions of a millimeter, making the initial cuts that establish the cant, or squared section, from which all other cuts will be derived. Following primary breakdown, cants move to the gang saws or twin band mills for secondary processing. Gang saws are fascinating pieces of equipment. Imagine a frame holding multiple parallel saw blades, all cutting simultaneously to slice a cant into multiple boards in a single pass. The precision required is extraordinary. Blades must remain perfectly parallel and tensioned correctly, or the resulting lumber will be unusable. The rhythmic up and down motion of a gang saw, processing log after log, represents manufacturing efficiency that would have seemed like magic to sawmill workers of the 1950s and 60s. The edger system comes next, trimming boards to consistent width and removing irregular edges. Modern edgers use overhead scanners to detect wane, that's bark or missing wood on the board's edge, and optimize each cut for maximum value. Automated positioning systems adjust the saw heads in real time, and the whole process happens so quickly that boards flow through at rates that would have required dozens of skilled workers in earlier decades. Now here's where Winstone Pulp International's integrated approach really shines. All the chips, sawdust, and offcuts from the Tangiwai sawmill are collected and transported to their Karioi pulp mill. Nothing goes to waste, a principle that old-time operators understood but couldn't implement as completely without modern transportation and processing capabilities. At the Karioi pulp mill, the wood chips from Tangiwai, along with specially prepared pulpwood logs, begin their transformation into paper pulp through the kraft pulping process. This chemical pulping method, developed in Germany in the 1870s and perfected over decades, uses a mixture of sodium hydroxide and sodium sulfide, called white liquor in the industry, to break down the lignin that binds wood fibers together. The process begins with the chip screening and washing systems. Chips must be uniformly sized because inconsistent chip dimensions lead to uneven cooking and poor pulp quality. Vibrating screens separate oversized and undersized chips, with the accepts moving forward to the digesters. These pressure vessels are where the actual pulping magic happens. Chips in white liquor are cooked together at temperatures around 170 degrees Celsius and pressures exceeding 100 psi for several hours. The lignin dissolves, separating the cellulose fibers that will become paper pulp, while the chemicals are recovered for reuse, an environmental and economic necessity in modern pulp production. This integrated operation, from log to lumber at Tangiwai and residuals to pulp at Karioi, represents the evolution of an industry that's been transforming forests into useful products for centuries, now doing it with unprecedented efficiency and environmental consciousness. Continuing our exploration of world-class sawmill operations, we're heading to a BSW facility that showcases some of the finest Italian engineering in the wood processing industry. BSW, which stands for Bayerische Sägewerksgesellschaft, that's Bavarian Sawmill Company for those of us who don't speak German, has been processing timber since the 1800s, and their adoption of Primultini equipment represents the marriage of traditional European craftsmanship with cutting-edge automation technology. For those unfamiliar with the name, Primultini is one of Italy's premier manufacturers of sawmill equipment, with a reputation built over generations for producing machinery that combines precision, durability, and innovative design. When you see Primultini equipment in action, you're watching the culmination of decades of engineering refinement focused on a single goal: extracting maximum value from every log that enters the mill. The BSW operation we're examining today processes primarily softwood species, spruce, pine, and fir, which are the backbone of construction lumber markets throughout Europe and beyond. These species have been the workhorses of the building industry for centuries. If you've ever renovated an old American home, you've probably encountered tight-grained pine or fir lumber that's still solid after 100 years or more. Modern processing techniques ensure today's lumber meets even higher standards than those old-growth timbers. Let's walk through this facility's workflow, starting where every sawmill operation begins: log intake and sorting. The Primultini log sorting system uses a combination of mechanical and optical technologies that would seem like science fiction to sawmill operators from just a generation ago. Logs arrive on a deck where they're measured for length and diameter using laser scanning systems. Each log is then assigned to a specific processing line based on its characteristics. Larger, higher quality logs go to lines optimized for producing premium structural lumber, while smaller or lower grade logs are directed to lines configured for producing boards, pallets, or processing into chips. The debarking drums in the system are particularly impressive. Unlike ring debarkers that work on individual logs, drum debarkers can process multiple logs simultaneously. Logs tumble inside a large rotating cylinder lined with metal teeth or chains, with the bark being literally scraped and knocked off through mechanical action. It's more aggressive than ring debarking, but incredibly efficient for high-volume operations. The removed bark, as you might expect, doesn't go to waste. It's collected for use as landscaping mulch or biomass fuel. After debarking, we encounter one of Primultini's signature innovations: their log positioning and optimization system. This is where things get really interesting from a technical standpoint. The system includes multiple cameras and laser sensors positioned around the log infeed, capturing thousands of data points to create a complete three-dimensional profile. But here's what sets Primultini's system apart. Their software doesn't just look at the log's external shape. It uses advanced algorithms to predict internal characteristics based on external indicators, things like branch patterns, growth rings visible at the log ends, and even subtle color variations in the wood that might indicate defects or density changes. This predictive capability means the system can optimize cutting patterns, not just for what it sees, but for what it expects to find inside the log. For operators, this translates to fewer surprises and better lumber recovery. It's the kind of sophisticated analysis that experienced sawyers used to do by eye and intuition, now performed by computers in milliseconds with consistency that human operators, no matter how skilled, simply cannot match over thousands of logs per day. The main breakdown line features Primaltini's Profile Chipper Canter, a machine that represents one of the most significant advances in sawmill technology of the past few decades. Here's how it works. As the log enters the chipper canter, it's held firmly by feed rollers, while large, specialized cutting heads, essentially heavy-duty profiling chippers, remove the rounded outer portions of the log, creating flat surfaces and establishing the cant. Following the chipper canter, cants move to Primaltini's gang saw or multi-blade circular saw systems. The gang saw configuration at this BSW facility is particularly impressive. It can hold up to a dozen blades simultaneously, allowing it to convert a cant into multiple boards in a single pass. The frame that holds these blades must be incredibly rigid, as even microscopic deflection would result in wavy boards. Primaltini achieves this rigidity through precision machined steel frames and sophisticated tensioning systems that keep each blade exactly where it needs to be, even under the tremendous forces generated during cutting. The saw blades themselves are engineering marvels. They're not simple flat pieces of steel. They're carefully tensioned, meaning the steel is stressed in specific patterns, so that when the blade heats up during cutting, it maintains its flatness. After gang sawing, boards proceed to Primaltini's edger system, which represents another area where Italian engineering excellence shines. The edger uses servo-driven saw heads that can reposition themselves in fractions of a second, responding to real-time data from overhead scanners. As each board passes beneath the scanners, the system evaluates its width, identifies the cleanest edges, and positions the saws to maximize the usable width while removing defects. This all happens so fast that boards flow through at steady speeds, with the saws dancing back and forth in a precisely choreographed mechanical ballet. The trimmer system, positioned downstream from the edger, performs similar optimization for board length. Multiple saws, positioned along the board's travel path, cut simultaneously, dividing each piece into the most valuable length combinations possible. A 16-foot board might become one 12-footer and one 4-footer, or two 8-footers, depending on defect locations and market demand. The software managing these decisions considers current lumber prices for different lengths, updating its optimization strategies as market conditions change. What's fascinating about this entire Primaltini-equipped BSW operation is how it exemplifies modern manufacturing philosophy: maximum automation for consistency and efficiency, combined with maximum flexibility to adapt to varying raw materials and changing market demands. It's a far cry from the fixed, inflexible production lines of mid-20th century industrial operations, and it points toward an even more adaptive future for sawmilling. We're concluding our exploration of advanced sawmill operations with a visit to Prime Sawmill in Gisborne, New Zealand, a facility that perfectly illustrates how modern sawmilling has evolved into a sophisticated blend of engineering, information technology, and good old-fashioned lumber craftsmanship. Let's begin our tour at the log yard, where the fundamental character of this operation becomes immediately apparent. Prime Sawmill processes logs ranging from small diameter pulpwood to large saw logs exceeding 400 millimeters in diameter. That's roughly 16 inches for those of us still thinking in imperial measurements. The log intake system uses a combination of hydraulic loaders and conveyor systems that would be familiar in concept to anyone who worked in sawmills during the 1960s and 70s, but the execution is thoroughly modern. Logs are lifted from storage piles and placed onto the in-feed deck where they're initially measured and assessed. What's changed dramatically is the sophistication of that assessment. Where older systems relied on workers physically measuring logs with tape measures and marking them with crayon or paint, Prime's system uses laser scanning and machine vision to characterize each log automatically. The scanning happens in stages. First stage scanners capture overall dimensions: length, diameter at small end, diameter at large end, and sweep or curvature. Second stage scanners look for specific features: branch knots, surface defects, splits, and discoloration that might indicate internal problems. All this data feeds into the mill's optimization software, which will direct how each log is processed. It's worth noting that this technology has been refined over decades. Early scanning systems, introduced in the 1980s, were crude by today's standards and required extensive manual oversight. Debarking at Prime Sawmill utilizes a high-pressure water debarking system for a portion of their logs, particularly during warmer months when bark is easiest to remove. This method, less common than mechanical debarking but highly effective, uses water jets at pressures exceeding 1/500 psi to blast bark away from the wood. For logs processed during winter months or those with tighter bark, Prime uses a ring debarker as backup. This flexibility in processing methods, having multiple approaches available for different conditions, represents mature operational thinking. The old approach was to have one method and make it work regardless of circumstances. Modern operations recognize that flexibility, though it requires additional capital investment, delivers better overall results. The heart of Prime Sawmill's operation is their main saw line, a configuration that combines the best elements of European and North American sawmill design philosophy. The log positioning system uses individually controlled hydraulic arms that can rotate, center, and position each log with extreme precision before it encounters the cutting equipment. Watching this system work is like observing a very large, very precise robot arm, which, in essence, is exactly what it is. Each log is positioned based on the optimization solution calculated by the scanning system, rotated to present the best face toward the saw, and fed into the cutting zone at precisely controlled speeds. The primary breakdown saw at Prime is a large diameter bandsaw, a choice that reflects the facility's focus on producing high-value lumber from quality logs. Bandsaws have several advantages for this application. Their thin curve, typically around 3 to 4 millimeters, wastes less wood than circular saws, which is particularly important when processing expensive logs. Operating a production bandsaw is still considered one of the higher skill positions in modern sawmilling. The operator must monitor blade tension, which changes as the blade heats up during use, adjust saw speed and feed rate based on wood characteristics, and make constant small corrections to keep the blade cutting straight and true. Bandsaw blades are also remarkable pieces of engineering. They're essentially very long, very thin strips of high-grade steel formed into continuous loops, with teeth precisely ground along one edge. After primary breakdown, cants move to the quad bandsaw system, where 4 individual bandsaw heads can work simultaneously on a single cant. This is where Prime's operation really demonstrates the power of modern automation. Each of the 4 saw heads can be positioned independently, allowing the system to cut boards of different thicknesses from the same cant in a single pass. Sensors detect the cant's precise position and dimensions as it enters, servo motors adjust the saw heads to their calculated positions, and the cant is cut into multiple boards in seconds. The boards then proceed to the edger line, which at Prime Sawmill includes some particularly interesting technology. In addition to the standard overhead scanners that identify board edges and defects, Prime's edger system includes grain angle sensors. These devices use laser optics to detect the angle of wood grain relative to the board's long axis, what sawyers call grain deviation or slope of grain. This matters because boards with excessive grain deviation are weaker and more prone to warping. The trimmer system at Prime is a flying cutoff design, meaning the saws themselves travel along with the boards as they're cut, maintaining continuous motion rather than requiring boards to stop for trimming. This increases throughput significantly and reduces wear on the conveyor systems. Multiple saws can engage simultaneously, allowing complex cutting patterns that optimize value recovery. Beyond the main saw line, Prime Sawmill operates extensive sorting and grading systems. Green lumber, that's freshly sawn lumber that hasn't been dried yet, moves through a series of automated sorting stations where it's segregated by species, grade, dimension, and ultimately end use. This sorting was once done entirely by hand, with workers physically moving boards from conveyor to storage stack based on markings made by human graders. Today, much of that work is automated, though human graders still play crucial roles in quality control and handling exceptions that automated systems can't process. The lumber then moves to kiln drying facilities, where moisture content is reduced from around 60 to 80% in green lumber to 15 to 19% for typical construction applications, or even lower for specialized uses. Kiln drying is both art and science. Dry too fast and lumber warps, splits, or develops internal checking. Dry too slowly, and productivity suffers while lumber quality may be compromised by fungal staining. Watching Prime Sawmill operate reminds us that while the fundamental task, converting round logs into rectangular lumber, hasn't changed since humans first split logs with wedges thousands of years ago, the sophistication with which we accomplish that task continues to evolve. It's a testament to human ingenuity and our endless drive to do things better, faster, and more efficiently.